The moon is slowly drifting away from us. This single fact reveals a hidden force that governs every world in the cosmos. I am talking about tidal evolution, the slow-motion gravitational dance that can pull celestial bodies together or push them irrevocably apart. By the end of this journey, you will understand the invisible mechanics that decide the ultimate fate of moons, planets, and even stars. We will see how this process could forge hidden oceans on distant moons, and how it might one day allow us to engineer entire orbits. What forgotten rhythm do the heavens truly keep? This gentle stretching of a world is the cosmic signature of a tidal force. Think of our own ocean tides, that rhythmic rise and fall you see at the beach. That is not just water moving, it is the entire planet being subtly deformed by the moon's gravity. The side of Earth facing the moon feels a stronger pull than the far side, and this difference stretches our world, creating a slight bulge in the rock and water both toward and away from our companion. The same force on a far grander and more rigid scale is what slowly sculpts the orbits of distant worlds. Now visualize a simple sphere, a planet or a moon. As it feels this uneven pull from a neighbor, it does not remain a perfect ball. It is gently squeezed and stretched, becoming a little more like an American football, an ellipsoid with two bulges. One bulge points toward the gravitational source and one points directly away. This is the tidal bulge, but here is where the story gets interesting. If the stretched world were perfectly still, these bulges would line up neatly with its partner. However, almost every world spins. It rotates on its own axis. And that spin often moves the bulges out of perfect alignment. Imagine spinning a water balloon. The water inside sloshes and shifts, lagging slightly behind the spin. A similar thing happens with a planet's tidal bulge. It does not point perfectly at its partner. It is dragged a little bit ahead or behind by the world's own rotation. That tiny misalignment, that slight offset of the bulge is everything. It is the hidden engine of tidal evolution, because now the gravitational pull between the two bodies is no longer perfectly symmetrical. That off-center bulge creates a persistent gravitational tug, a constant nudge that ever so slowly changes the energy of the orbit. It is this relentless, subtle force that begins the great celestial dance of orbital decay or expansion. That off-center bulge is not just a passive shape, it is an active force. Think of it as a handle, a grip that one celestial body has on another. Because the bulge is slightly ahead or behind the line between the two worlds, its own gravity tugs back on the primary body. This creates a constant, gentle torque, a twisting force. It is as if the stretched world is perpetually applying a tiny brake or perhaps a gentle push to its partner. This is the fundamental mechanism, the hidden hand that reshapes solar systems over eons. The key to understanding what happens next lies in a concept called angular momentum. You can think of angular momentum as the spin energy of a rotating or orbiting object. A spinning ice skater who pulls their arms in spins faster, they concentrate their angular momentum. When they extend their arms, they slow down, spreading that same energy out. Crucially, in a closed system like a planet and its moon, the total amount of angular momentum is conserved. It cannot be created or destroyed, only transferred from one place to another. This is what the tidal torque does. It acts as a cosmic siphon, moving angular momentum from the spin of the bodies into their shared orbital motion, or sometimes the other way around. The direction of this transfer depends entirely on one critical factor, the relative speeds of rotation and revolution. Our own Earth-Moon system provides the classic example. Earth rotates on its axis once every 24 hours. The Moon, however, takes nearly 28 days to complete one orbit around us. Earth spins faster than the Moon orbits. Because of this, Earth's rapid rotation drags its tidal bulge slightly ahead of the direct line to the Moon. That forward-leaning bulge then pulls gravitationally on the Moon, giving it a tiny forward tug in its orbit. This transfers angular momentum from Earth's spin to the Moon's orbit. The result, Earth's rotation very gradually slows down, making our days longer by a tiny fraction of a second each century. And the Moon, receiving that extra energy, spirals slowly outward, expanding its orbit by about 3.8 centimeters per year. The system is evolving toward a state of tidal locking, where Earth's rotation would eventually slow to match the Moon's orbital period, a day lasting a month. But not all systems follow this path of expansion. Imagine the opposite scenario. Picture a Moon that orbits its planet faster than the planet spins. This is common for moons very close to their giant hosts, like Jupiter's innermost moon, Io. In that case, the Moon's swift motion means the planet's tidal bulge is dragged slightly behind, lagging the line between them. That lagging bulge now pulls backward on the Moon, acting as a brake. Angular momentum is siphoned from the Moon's orbit and injected into the planet's spin. The Moon loses orbital energy and its orbit begins to shrink. It spirals inward, a process we call orbital decay. This is the great fork in the cosmic road, decided by a simple race between spin and orbit. One path leads to a slow, graceful drift into the darkness. The other leads to an increasingly intimate and often violent dance, drawing two worlds toward an inevitable, final embrace. The path of orbital decay is a celestial countdown. This is the inward spiral where a moon's orbit steadily shrinks, drawing it closer to its planet with every passing century. The condition for this fate is the inverse of our own moon story. Orbital decay occurs when the Moon orbits its planet slower than the planet spins on its axis. In this cosmic race, the planet's rotation wins, dragging its tidal bulge ahead of the line pointing to the slower-moving Moon. That forward-leaning bulge creates a gravitational pull that is anything but helpful. Instead of giving the Moon a gentle push forward, it actually tugs on it from an angle, pulling it slightly along its direction of motion. This might sound like it should speed the Moon up, but in orbital mechanics, this peculiar forward tug acts as a brake. It siphons angular momentum out of the Moon's orbit and transfers it into the planet's already faster spin. With its orbital energy being steadily drained, the Moon cannot maintain its altitude. It begins to lose altitude, spiraling inexorably inward. This spiral is not a rapid plunge, but a slow, relentless descent over millions of years. Where does it end? The final act depends on the Moon's composition and its proximity to the planet's overwhelming gravity. One possibility is tidal disruption. As the Moon ventures too close, the difference in gravitational pull between its near side and far side becomes so severe that the Moon is literally pulled apart. It stretches and fragments, its pieces spreading out to form a new ring system around the planet, a glittering tombstone of what once was a world. The other, more direct end is a catastrophic collision, a final merger with the planetary surface. But there is a boundary before either fate, known as the Roche limit. This is the orbital distance within which a moon's own gravity can no longer hold itself together against the planet's tidal forces. Inside this limit, destruction is guaranteed. We are not just talking about theoretical futures. Look at the Martian sky. The larger of its two moons, Phobos, is living on borrowed time. It orbits Mars faster than the planet rotates, placing it firmly in the grip of orbital decay. Today, Phobos draws about 2 meters closer to Mars every century. Scientists predict that in 30 to 50 million years, it will either be shredded into a ring of debris by the Martian Roche limit, or it will crash onto the rusty surface in a titanic impact. It is a stark reminder that the serene clockwork of the heavens has a dramatic and sometimes destructive cadence. While 2 meters closer per century may seem imperceptible, this decay is a relentless countdown for Phobos. Its orbit shrinks by roughly 1.8 centimeters every year, a slow but inescapable inward drift. The reason lies in that critical cosmic race between spin and orbit. Mars completes one rotation, a Martian day, in just over 24 hours. Phobos, however, races around the planet in a mere 7 hours and 39 minutes. The Moon orbits faster than the planet spins. This means the tidal bulge on Mars is dragged slightly behind the swiftly moving Moon. That lagging bulge exerts a gravitational pull that acts as a continuous brake on Phobos, steadily draining its orbital energy and causing its slow spiral toward the red planet. The final chapter for this moon is written in the unforgiving laws of gravity. In perhaps 30 to 50 million years, Phobos will approach the Martian Roche limit. Visualize this moment. As it crosses that threshold, the difference in Mars's gravitational pull between the Moon's near side and far side will become stronger than the force holding Phobos itself together. The Moon will not simply crash, it will be systematically torn apart. It will stretch and fragment, its rocky body disintegrating into a cascade of debris that will slowly spread into a broad, elegant ring around Mars. This new ring would be a temporary monument, lasting maybe 100 million years before the particles rain down onto the planet. Alternatively, if some of the larger fragments survive the initial breakup, they could still ultimately collide with the surface in a series of colossal impacts. This slow-motion study of a doomed moon is far more than a spectacle. It is a vital natural laboratory. By observing Phobos, we refine our understanding of tidal forces and orbital decay on a grand scale. The principles governing its fate are the same that dictate the long-term dynamics of every moon in our solar system and beyond. This knowledge even extends to our own technology, helping us predict the eventual decay of artificial satellites and plan for the stable orbits of future space stations. Phobos is a stark, real-time reminder that the orbits we see as permanent are merely snapshots in an endless celestial dance of construction and destruction. The story of Phobos is one of cosmic convergence, but the universe holds another, more serene path. Orbital expansion is the great drift apart, a slow-motion celestial divorce where a moon gradually spirals outward into the vastness of space. This process is the precise opposite of decay, governed by a flipped condition. Expansion occurs when the orbiting body, like our own moon, takes longer to circle its planet than the planet takes to spin on its axis. In this scenario, the planet rotates faster than the moon orbits. Our Earth, spinning once every 24 hours, is a whirlwind compared to the moon's leisurely 28-day orbit. This rapid spin drags Earth's tidal bulge slightly ahead of the direct line to the slower-moving moon. That forward-leaning bulge is the key. Its gravitational pull does not break the moon, but instead tugs on it from an angle, giving it a gentle forward nudge along its orbital path. This persistent nudge acts like a continuous boost, transferring angular momentum from Earth's furious spin into the moon's orbital motion. The cost is that Earth's rotation very slowly breaks, lengthening our day by a microscopic amount each century. The gain is that the moon, infused with that extra energy, must move to a higher, slower orbit. It spirals outward, receding from us at a rate of about 3.8 centimeters every year. It is a separation measured in the width of your thumb over a human lifetime, but compounded over millions of years. It represents a fundamental reshaping of our sky. This gentle drift is not a rebellion, but a natural evolution toward equilibrium. The system is moving toward a state called tidal locking, where the planet's rotation would eventually slow to match the moon's orbital period, and the two would face each other forever, like partners in a final, silent dance. While our moon is the textbook example, this process of expansion is a universal sculptor. It explains why many distant exomoons we hope to find may orbit far from their host planets, and it dictates the long-term fate of countless celestial partnerships across the galaxy. This gentle outward drift of our moon is not a theory, it is a measured fact. The proof was left on the lunar surface by human hands. During the Apollo missions, astronauts placed special mirrors called laser retroreflectors on the moon. For decades now, observatories on Earth have been firing powerful laser pulses at those mirrors. By timing the light's round-trip journey with incredible precision, down to a few picoseconds, we can measure the distance to the Moon with an accuracy of less than a centimeter. These ongoing experiments confirm it. The Moon is indeed moving away from us at about 3.8 centimeters each year. That is the width of your thumb, a tiny distance on a cosmic scale, but over the span of a human lifetime, it adds up to nearly 4 meters of separation. This measurement is the bedrock of our understanding of tidal evolution in our own celestial backyard. But where is that energy for the Moon's escape coming from? The answer is written in the lengthening of our days. It is a grand trade governed by the conservation of angular momentum we discussed earlier. As the Moon's tidal bulge pulls forward on our satellite, it transfers rotational energy from a spinning Earth into the orbital energy of the receding Moon. The cost is that Earth's spin is very gradually slowing down. Our planet is like a spinning ice skater who slowly extends their arms, causing their rotation to become more stately and slow. This braking effect is minuscule, adding about 1.7 milliseconds to the length of a day every century. It means that in the age of the dinosaurs, a day was only about 23 hours long. Compounded over billions of years, the change is profound. Now, let your mind travel forward across eons. In about 50 billion years, the cosmic dance will reach a kind of equilibrium. Earth's rotation will have slowed so much that one day will equal 1 month. The same hemisphere of Earth will forever face the Moon, just as the same face of the Moon now forever faces us. They will be tidally locked, a final, silent embrace in the sky. The Moon will hang motionless over one half of the world, a permanent fixture, while the other half of Earth will never see it again. By that distant time, the Moon will have receded to an orbit about 40% larger than it is today. This is the ultimate fate written into the gravitational fabric of our planet-Moon system, a slow, graceful pirouette toward a final, frozen pose. That final, frozen pose has a name: tidal locking. It is the ultimate destination for countless celestial dances, a state of perfect gravitational synchronization. Tidal locking occurs when an orbiting body's rotation on its axis slows so much that it exactly matches the time it takes to complete one orbit around its partner. The result is that the same hemisphere forever faces the primary world, just as our Moon eternally shows one face to Earth. This is not a coincidence or a quirk of our system. It is the natural end state of tidal evolution. The relentless tug of those off-center tidal bulges acts as a cosmic brake, gradually slowing a world's spin over billions of years until its rotation is perfectly matched to its revolution. At that point, the bulges finally align directly with the gravitational pull, the torque vanishes, and the orbital dance stabilizes. The push or pull stops, and the two worlds become fixed in each other's sky. Look around our own solar system, and you will see this is the rule, not the exception. Almost every major moon is tidally locked to its planet. Jupiter's Galilean moons, from volcanic Io to icy Europa, all keep one face pointed toward the gas giant. Saturn's Titan, with its thick atmosphere and methane lakes, does the same. These worlds are locked in a permanent gravitational embrace, their surfaces sculpted by forces that are forever fixed in place. But the implications reach far beyond our local moons. This process is crucial for understanding the most common potentially habitable worlds in our galaxy, planets orbiting red dwarf stars. These small, cool stars have habitable zones so close that an Earth-like planet would be tidally locked in a matter of millions of years. One side would be in perpetual, scorching daylight, while the other languishes in eternal, frozen night. The thin ribbon of twilight between them might be the only place life could cling on, a starkly different vision of habitability. Tidal locking is not an end but a transformation. It redefines the very nature of a world, dictating its climate, its geology, and perhaps even the possibility of life upon it. it is the silent, final sentence written by gravity on the story of so many cosmic partnerships. Tidal locking transforms the very idea of a habitable zone. For planets orbiting the small, dim stars known as M-dwarfs, the most common stars in our galaxy, the region where liquid water could exist is extraordinarily close. A world there would be bathed in gentle starlight but gripped by ferocious tidal forces. This proximity almost guarantees the planet would become tidally locked, one half in permanent daylight, the other in endless night. On the surface, this seems like a death sentence for life, a world of scorching deserts facing an airless, frozen wasteland. But the story does not end there, because those same tidal forces offer a surprising source of hope deep within the planet itself. The constant gravitational kneading from its star does not just lock the planet's rotation, it flexes its very crust and mantle. This flexing generates internal friction, a relentless heat known as tidal heating. Imagine repeatedly bending a metal paperclip. It grows warm to the touch. Now imagine that process on a planetary scale, operating continuously for billions of years. This internal furnace could be powerful enough to melt rock, driving volcanic activity, and most importantly, sustaining vast global oceans beneath a shell of ice. We see this in our own solar system on Jupiter's moon, Europa. Though locked to its planet, not a star, Europa is cracked and flexed by Jupiter's gravity, and scientists are confident a salty ocean sloshes beneath its icy crust, kept liquid by this very tidal heat. For a locked exoplanet, such a subsurface ocean, shielded from the harsh surface extremes, could be a sanctuary for life, yet the surface itself remains a puzzle. Could a thick, global atmosphere act as a planetary blanket, redistributing the star's heat from the day side to the frigid night side? Modern climate models suggest it is possible. A dense atmosphere with active weather patterns might prevent the atmosphere from freezing out entirely on the dark side, creating a more temperate, if alien, environment. This means a planet that appears from a distance to be a world of extremes could in fact harbor a stable, even global, biosphere. The search for life beyond Earth is no longer just about finding a planet at the right distance from its sun. It is about understanding the hidden, dynamic warmth of tidal forces and asking whether the most common planets in the galaxy, locked in a permanent embrace with their dim red suns, are not tombs but cradles. The search for life leads us to a world of fire and another of hidden seas. Look at Jupiter's moon Io, a landscape straight from a cosmic forge. Its surface is a chaotic canvas of yellow sulfur and black silicate rock, dotted with hundreds of active volcanoes that spew plumes hundreds of kilometers into space. Io holds a dramatic title. It is the most volcanically active body in our entire solar system. But this world is far too small to have retained the primordial heat from its formation. Its fiery heart is stoked by something far more dynamic, the relentless gravitational tug of war we call tidal heating. Jupiter's immense gravity, combined with the precise gravitational kicks from its sister moons Europa and Ganymede, constantly flexes Io's interior. Imagine squeezing a rubber ball rhythmically over and over. The friction inside generates heat. For Io, this process is so intense it melts rock on a global scale, creating vast subterranean magma oceans that erupt violently to the surface. This is tidal evolution in its most extreme and visible form, a moon being literally cooked from the inside out by the rhythm of its own orbit. Yet just next door, the same fundamental force paints a completely different picture. Europa, another of Jupiter's large moons, experiences a gentler but no less transformative version of this heating. Its icy surface is a cracked, fractured shell, resembling a cracked eggshell floating in space. Beneath this global ice crust, scientists are confident a vast saltwater ocean churns, containing more liquid water than all of Earth's oceans combined. What keeps this ocean from freezing solid in the deep cold of space? The answer, again, is tidal heating. As Europa orbits Jupiter, the gas giant's gravity flexes the Moon's icy shell and rocky core. This internal friction acts as a submerged furnace, providing enough warmth to maintain a liquid global ocean. This makes Europa one of the most promising places in our solar system to search for life beyond Earth. A hidden, watery world powered not by the distant sun, but by the gravitational embrace of its planet. The engine behind this spectacular heating on both moons is a celestial rhythm known as an orbital resonance. Io, Europa, and the moon Ganymede are locked in a precise gravitational dance called the Laplace resonance. For every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This means the moons regularly line up in the same configuration, their gravitational pulls reinforcing each other in a predictable rhythm. This resonance prevents their orbits from becoming perfectly circular. Instead, they maintain slight elliptical paths. When a moon moves closer to Jupiter in its elliptical orbit, the giant planet's gravitational squeeze intensifies, stretching the moon more. As it swings farther out, the squeeze relaxes. This periodic flexing, driven by the resonant clockwork of the 3 moons, is what generates the tremendous internal friction and heat. Without this coordinated dance, Io might be a cold, dead rock, and Europa's ocean would have frozen over eons ago. It is a breathtaking demonstration of how orbital mechanics do not just dictate paths in the sky, but can forge the very nature of worlds, turning some into volcanic hellscapes and others into potential havens for life. This precise gravitational rhythm is a cosmic metronome, amplifying the tidal forces to extraordinary levels. Orbital resonances occur when the orbital periods of 2 or more bodies lock into a simple, repeating ratio, like 1 to 2 or 2 to 3. It means for every time one body completes its orbit, the other completes exactly 2 or 3, and so on. This creates a predictable pattern where the bodies regularly line up at the same points in space, giving each other a consistent gravitational nudge at the same orbital location. Think of pushing a child on a swing. If you push at random times, the swing might wobble. But if you push at exactly the right moment in its arc, every single time, the energy adds up efficiently and the swing goes higher and higher. Orbital resonance works the same way. Those perfectly timed gravitational kicks do not cancel out, they reinforce each other, pumping energy into the system with incredible efficiency. This is the secret behind the extreme tidal heating we see on moons like Io and Europa. Their orbits are not just elliptical, they are locked in a resonant chain. For every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This 1 to 2 to 4 resonance means these moons repeatedly align in a specific configuration, their combined gravitational pulls rhythmically tugging on each other. This resonant dance prevents their orbits from circularizing, maintaining the elliptical paths that are crucial for tidal heating. As Io moves closer to Jupiter on its elliptical path, the pull is strongest and the moon is stretched maximally. When it swings back out, it relaxes, but because of the resonance, the kicks from Europa and Ganymede ensure this stretching happens with a powerful, regular beat. This turns the gentle tidal flexing into a continuous planet-scale workout, generating the immense internal friction that melts Io's interior and warms Europa's hidden ocean. Resonances are not just about creating heat, they are fundamental architects of solar system stability. A resonance can act as a protective lock, stabilizing orbits over billions of years by preventing chaotic interactions. We see this with Pluto and Neptune, whose orbits are in a stable 3 to 2 resonance, ensuring they never collide. Conversely, resonances can also be agents of chaos. Gaps in Saturn's rings are carved out by resonances with its moons, where the regular gravitational kicks eject ring particles entirely. Understanding these resonant relationships is the key to deciphering the complex, multi-body dances we see throughout the cosmos, from the moons of Jupiter to the planets orbiting distant stars. This gravitational choreography does not stop at planets and moons. Lift your gaze to the scale of entire suns, and you will witness a stellar waltz of breathtaking power. In the deep reaches of space, two stars can orbit one another in a tight embrace, forming a binary system. Here, the principles of tidal evolution are magnified to a cosmic crescendo. Each star exerts a colossal gravitational pull on its partner, stretching it, distorting its perfect spherical shape into a teardrop or an ellipsoid. Just as with moons and planets, this tidal distortion, if misaligned by the star's spins, creates a torque that transfers angular momentum. Over millions of years, this relentless interaction can synchronize their spins with their orbit, leading to a spectacular state of mutual tidal locking, where both stars forever show the same face to each other, eternally bound in a fiery gaze. This tidal dance also smooths out the rough edges of their motion. The constant gravitational friction works to circularize their orbits, transforming any initial elliptical path into a near-perfect circle. But the most dramatic consequence occurs when the stars are so close that one star's gravity begins to steal the very substance of the other. Each star has a gravitational territory called its Roche lobe, a bubble of space where its own gravity dominates. In an intensely close binary, one star can swell and evolve to fill this bubble. Once it overflows this boundary, its outer layers are no longer bound to it. They stream across the void, siphoned by gravity onto the waiting companion star in a process called Roche lobe overflow. Imagine a celestial fountain where an entire ocean of stellar plasma arcs from one sun to another. This transfer of mass completely rewrites the system's destiny. The donor star is stripped down, potentially revealing a dense core. The receiving star is rejuvenated with fresh fuel, but it can also become unstable. For certain binary pairs, especially those containing a white dwarf, this slow theft of matter can have a cataclysmic end. If enough mass accumulates on the white dwarf, pushing it over a critical threshold, it can ignite a runaway thermonuclear explosion so violent it obliterates the entire star. We see this as a Type Ia supernova, a standard candle that lights up galaxies. In other systems, the tidal evolution and mass transfer might spiral two ultra-dense remnants like neutron stars, closer and closer until they finally merge in a collision that shakes the fabric of spacetime itself, sending out ripples we detect as gravitational waves. From a gentle locking of spins to the violent birth of cosmic lighthouses, tidal evolution scripts the final, fiery acts for stars dancing too close together. The silent theft of mass between stars is a prelude to something even more profound. When the dance partners are the universe's most extreme objects, the final act of tidal evolution is written not in light but in the shuddering of spacetime. We are now listening to the cosmos with an entirely new sense, detecting the faintest whispers of orbital decay on a scale that defies imagination. These whispers are gravitational waves, ripples in the very fabric of reality predicted by Einstein over a century ago. They are generated when massive objects accelerate, especially when they orbit each other in a tight, violent embrace. Every pair of neutron stars or black holes locked in a mutual orbit is essentially a spinning dumbbell of unimaginable mass. As they whirl around each other at a significant fraction of light speed, they churn the spacetime around them, sending out waves that travel at light speed across the universe. But here is the crucial link to our story. The emission of these waves carries energy away from the binary system. That energy loss is orbital energy. With each ripple that escapes, the two objects lose a tiny bit of their momentum, forcing them to spiral closer together. This is orbital decay driven not by tidal bulges, but by the direct radiation of gravity itself. For most of the binary's life, this spiral is glacially slow, but as the orbit shrinks, the dance accelerates and the emission of gravitational waves becomes stronger. This creates a runaway feedback loop of decay. The closer they get, the more powerful the waves, and the more powerful the waves, the faster they decay. The final moments are a crescendo of motion. Listen to the sound of a discovery. This is a sonification of the gravitational waves detected by LIGO and Virgo from two neutron stars colliding. What you hear is the orbital decay process itself, translated into sound. The signal begins as a low hum, the slow, early inspiral. Then, over just a few seconds, the pitch rapidly rises and the volume swells. This is the famous chirp, the sound of the orbit tightening at a blinding pace as the stars complete thousands of revolutions in their final moments before merger. That rising chirp is the direct observational signature of orbital decay happening in real time, across more than 100 million light-years. It is the universe's most extreme demonstration of a fundamental truth: no orbit is forever when energy can escape. The final, cataclysmic merger is the period at the end of a sentence written in gravity, a fleeting burst of energy that forges gold, platinum, and other heavy elements, scattering them across the cosmos. We are no longer just observers of tidal evolution, we are listeners to its most violent and beautiful song. That final, cataclysmic merger is one possible end, but there is another, more serene and beautiful fate. Orbital decay can lead not to a collision but to a transformation, a celestial body reborn as a masterpiece of cosmic light and shadow. We call these planetary rings. They are the elegant, lasting aftermath of tidal destruction. The process begins when a moon, driven inward by orbital decay, crosses a critical boundary known as the Roche limit. This is the distance from a planet where the difference in gravitational pull between the near side and far side of the moon becomes stronger than the gravity holding the moon itself together. Inside this limit, the moon is no longer a single object. It is subjected to a relentless, stretching force. Imagine you are holding a clump of wet sand. If you pull gently from both ends, it might hold its shape, but if you pull with enough force, the clump will stretch and then tear apart in the middle. That is what happens to a moon inside the Roche limit. The planet's gravity pulls more strongly on the side of the moon closest to it and less strongly on the far side. This tidal force literally overcomes the moon's own self-gravity, the force that binds its material into a sphere. The moon is stretched into an elongated shape and then it fragments. It does not explode, it is systematically dismantled, torn into countless pieces from dust grains to boulders. This debris does not simply fall onto the planet. Each fragment now enters its own independent orbit around the planet, following the path the original moon was on at the moment it broke apart. Because the fragments were all part of the same object, their orbits are very similar, forming a broad, flat disk that encircles the planet's equator. This is the birth of a ring system. The most spectacular example in our solar system is, of course, Saturn. Its rings are a breathtaking band of ice and rock, spanning nearly 300,000 kilometers in width, yet in many places they are astonishingly thin, perhaps only 10 meters thick. They are not solid sheets, but trillions of individual particles, each orbiting Saturn like a tiny moon. While their beauty is timeless, their existence may be surprisingly fleeting. Recent evidence from the Cassini mission suggests Saturn's rings are relatively young, perhaps only 100 million years old, a mere blink in cosmic time. The leading theory is that they formed from the tidal disruption of a large, icy moon that wandered too close to the giant planet. The pristine ice that makes the rings so reflective hints at this recent, violent origin. Looking forward, we can see a ring system in the making. Mars's moon Phobos, locked in its slow orbital decay, is destined for this very fate. In 30 to 50 million years, as it approaches the Martian Roche limit, it will be pulled apart. The rubble will spread into a faint, dusty ring around the red planet, a temporary crown that will eventually rain down onto the surface over millions of years. Rings are not permanent monuments, they are ephemeral art, a final, dazzling performance by a moon that danced too close. But what if we could move beyond observation and become the architects of these celestial tides? The same gravitational forces that doom moons and sculpt worlds could one day become tools in our hands. For a civilization mastering its solar system, tidal evolution is not just a natural process to study. It is a fundamental engineering challenge and perhaps the ultimate key to stability. Consider the dream of immense orbital habitats, vast rotating cylinders or rings designed to house millions. Placing such a megastructure in a simple orbit around Earth might seem sufficient, but over centuries, the subtle tugs of the Moon, the Sun, and Earth's own imperfect shape would perturb its path. Left unchecked, these perturbations could lead to a slow, fatal orbital decay. The solution is active orbital maintenance, using gentle, continuous thrust to nudge the habitat back into its designated lane. But a more elegant, passive solution might harness tidal forces themselves. By carefully designing the structure's shape and mass distribution, engineers could theoretically create a gravitational interaction with Earth that is self-correcting, using the planet's own tidal pull to stabilize the station's position, a perpetual dance held in perfect balance. This is the first step toward tidal engineering, moving from prevention to deliberate design. The ambition grows with concepts like orbital plates or ring worlds, artificial bands encircling a star. Here, tidal forces are not a minor nuisance, they are the dominant, potentially shattering force. Any such structure would need to be in a precise orbit where the gravitational pull from the star is perfectly balanced by the ring's own rotational motion, creating artificial gravity on its inner surface. But if the ring is even slightly off-center, the star's gravity would pull more strongly on the closer side, creating a catastrophic tidal force that would rip the entire megastructure apart, sending it crashing into the Sun. Stability would require not just perfect construction, but potentially a system of active mass blocks or thrusters running continuously to correct any drift, an eternal vigil against the universe's desire to tear it down. This is engineering on a godlike scale, where understanding tidal evolution is the difference between building a new home for civilization and constructing its most spectacular tomb. The ultimate expression of this control would be direct tidal engineering of celestial bodies themselves. Imagine a future where we need to adjust the orbit of a metal-rich asteroid to bring it into a stable, accessible position for mining. Instead of using massive rockets, we could employ gravitational trickery. By placing a series of smaller, precisely weighted spacecraft in strategic orbits around the asteroid, their combined gravitational tugs could act like a distributed tidal force, gradually nudging the asteroid's trajectory over years or decades. This method, called a gravity tractor, is a form of slow, deliberate tidal evolution. On an even grander scale, consider terraforming a moon like Mars's Phobos. Instead of letting it be torn apart, a future civilization might use similar techniques to gently break its orbital decay, stabilizing it permanently as a scientific outpost or a gravitational anchor for a space elevator. We could even envision deliberately moving a small, icy moon from the outer solar system into an orbit around a dry, inner planet, using its tidal heating to melt its ice and create a new atmosphere over millennia. This is planetary management of the highest order, where we graduate from being passive inhabitants of a solar system to becoming its active stewards, using the gentle, relentless laws of gravity as our chisel to sculpt the heavens themselves. Our mastery of celestial tides leads us to a haunting cosmic silence. The universe is unimaginably vast and ancient, filled with billions of stars like our Sun, many with their own planets. By probability alone, the galaxy should be teeming with intelligent civilizations, yet we hear nothing. This contradiction is known as the Fermi paradox, the great silence that stands against our expectations. One compelling answer suggests there are filters, great barriers that prevent life from advancing to the stage where it can communicate across the stars. What if one of the most formidable filters is not biological but gravitational? What if the very process of tidal evolution, by locking planets to their stars, quietly snuffs out the candle of complex life before it can truly begin? The most common stars in the Milky Way are M-dwarfs, small, cool, and long-lived. Their habitable zones where liquid water could exist are extraordinarily close in. Any Earth-sized planet orbiting there would be swiftly tidally locked, one face in permanent, blistering daylight, the other in endless, frozen night. This creates a world of profound extremes. The atmosphere itself is at risk. On the frigid night side, gases like carbon dioxide and nitrogen could freeze out, falling as snow and collapsing the atmospheric pressure to near zero. The entire atmosphere could migrate and freeze on the dark hemisphere, leaving the dayside a bare, airless desert. Even if a thick atmosphere persists, the planet faces another threat from its temperamental star. M-dwarfs are notorious for violent stellar flares, eruptions of radiation that can strip away atmospheres and bathe the surface in deadly ultraviolet and X-rays. A planet locked so close has no magnetic field strong enough to reliably deflect such an onslaught. For any life trying to gain a foothold on the surface, these conditions seem insurmountable. This could be the filter. Simple, microbial life might survive in niche refuges, but the stable, long-term conditions needed for the evolution of complex organisms, ecosystems, and ultimately intelligence may be brutally rare on such worlds. The cosmic dice are loaded, and tidal locking may be the house rule that keeps the galaxy quiet. Yet hope is not lost, it simply moves underground, or rather under ice. The same tidal forces that lock the planet could provide a salvation beneath its surface. The gravitational kneading from the star generates internal heat, potentially maintaining a global liquid ocean beneath a thick crust of ice, just like on Jupiter's moon Europa. In such a subsurface ocean, shielded from stellar flares and extreme temperatures, the basic ingredients for life could mix for billions of years. Life could flourish there, perhaps even evolve into complex forms. But could it ever become a technological civilization? Could creatures swimming in a dark, subsurface sea ever discover fire, smelt metal, or build radio telescopes? The leap from a hidden aquatic world to one that looks up at the stars and wonders might be the second, even more difficult filter. The great silence may not mean we are alone. It may mean that the universe is full of hidden, thinking oceans, forever separated from the stars above by a ceiling of ice and the unyielding laws of tidal gravity. That hidden ocean might never build a telescope, but its existence hints at a profound truth. The forces that shape worlds can also be turned to our will, not just for creation, but for our own survival. This brings us to the ultimate test of our understanding: planetary defense. The threat is real, a mountain-sized asteroid on a collision course with Earth. The classic Hollywood solution is to blow it apart, but that often creates a shotgun blast of debris, trading one massive impact for many. A more elegant and perhaps more reliable strategy borrows directly from the principles of tidal evolution. It is called the gravity tractor. Imagine a spacecraft not much larger than a family car sent to rendezvous with the threatening asteroid. It does not land. Instead, it positions itself nearby and simply hovers, using gentle ion-electric thrusters to maintain a precise, stable distance. The spacecraft's mass is tiny compared to the asteroid, perhaps only a few tons against billions. But gravity is patient and cumulative. The minuscule gravitational attraction between the spacecraft and the asteroid creates a persistent, invisible tether. By holding its position, the spacecraft exerts a constant, gentle pull. Over months or years, this microscopic tug, applied continuously in the same direction, can ever so slowly alter the asteroid's velocity, just a few centimeters per second. In the vastness of space, that tiny change in speed, applied early enough, adds up to a massive shift in position over time, enough to turn a direct hit into a clean miss by thousands of miles. It is a defense system built on patience and precision, using the same fundamental force that drives moons together or apart. This is not classical tidal bulging, but it is a deliberate, controlled application of sustained gravitational interaction, a cousin to the grand tidal forces we have been exploring. For more urgent threats or larger asteroids, we might need to be more assertive. This is where truly tidal concepts come into play. One speculative idea involves using mass drivers, essentially powerful electromagnetic railguns mounted on the asteroid's surface. They would not blow the asteroid up, they would mine it, by firing a steady stream of the asteroid's own material into space like a rocket exhaust. The recoil would push the asteroid gradually off course. But we could go a step further. What if we used those mass drivers or even focused solar mirrors to create artificial tidal stresses? By systematically heating one specific region on the asteroid's surface, we could induce outgassing, where subsurface ices turn to vapor and jet into space like a natural rocket engine. By carefully controlling where and how this happens, we could generate a sustained directional nudge. An even more advanced concept involves using a powerful spacecraft to gravitationally tow a smaller asteroid into a resonant orbit with the threatening one, setting up a series of precise gravitational kicks over time that would gently deflect the larger body, a celestial game of gravitational billiards. These methods transform the asteroid from a passive projectile into an active part of its own deflection, using its own mass and composition against it. They move us from brute force to a nuanced understanding of celestial mechanics, where the most powerful tools are not explosives, but gravity, light, and time. The silent defense of our own world points to a deeper, slower rhythm, one that will ultimately rewrite the entire solar system. To understand our true cosmic destiny, we must zoom out to a scale of billions of years, forecasting the long-term tidal evolution of everything we know. The primary architect of this distant future will not be the planets but our own sun. As it ages, the sun will exhaust the hydrogen fuel in its core and begin to swell into a red giant star. This transformation is not just a change in color and size, it is a fundamental shift in mass and gravity. During its red giant phase, the sun will lose a significant portion of its mass, perhaps up to half, through a powerful stellar wind. This mass loss has a profound effect on the planets. The gravitational grip of the entire solar system weakens. According to the laws of orbital motion, as the central mass decreases, the planets must respond by moving outward, their orbits expanding to conserve angular momentum. Earth, Mars, Jupiter, all will spiral slowly away from the dying sun. But this grand migration is only the backdrop for a more intricate tidal drama playing out among the giant planets and their moons. As Jupiter and Saturn drift into the colder, darker reaches of the expanded solar system, the delicate gravitational balances that govern their moon systems will be perturbed. The intricate orbital resonances, like the one that heats Io and Europa, could be broken or newly forged. Some moons, caught in a gravitational tug of war between their planet and the sun's weakening pull, could be flung from their orbits entirely, ejected into the interstellar dark as rogue moons. For other moons, the changing dynamics could lead to a different fate, a shift into a more eccentric orbit driven by these new gravitational influences would intensify tidal flexing. A moon like Europa, with its subsurface ocean, might experience a surge of internal heating, potentially turning its icy shell into a global geyser field or even melting it entirely for a time, before the heat source fades and a new, thicker crust of ice refreezes. Meanwhile, the sun itself, in its final act, will exert monstrous new tidal forces. In its bloated red giant state, its outer atmosphere will extend to perhaps the orbit of Earth. Any inner planet that has not been consumed will be enveloped in a diffuse, hot plasma. The drag from this material, combined with extreme tidal forces, will circularize and decay the orbits of these worlds, dooming them to a final spiral into the stellar core. The outer solar system will become a ghostly realm. The gas giants, now distant and cold, will likely retain their retinues of major moons, though their orbits may be wider and their tidal relationships forever altered. The beautiful, youthful rings of Saturn will have long since darkened and dissipated, their ice particles eroded by micrometeorites or dragged down onto the planet. What remains is a dynamic, evolving portrait not of permanence but of continuous change. Our solar system, in 1 billion years, will be as different from today as the early, chaotic solar system was from the stable clockwork we see now. The great tidal forces are the slow hands of this cosmic clock, patiently reshaping our celestial neighborhood on a timescale that dwarfs mountains, continents, and all of human history. The silent clockwork of tidal evolution unfolds over timescales no human can witness. To grasp its full story, we must build a universe inside a machine. This is the realm of supercomputers, where astrophysicists run the most sophisticated simulations ever conceived to model the slow-motion dance of worlds. These are not simple animations, they are complex mathematical universes governed by the precise laws of gravity, physics, and tidal friction. At their heart are what we call n-body simulations. The n stands for the number of objects in the model, whether it is a star with 3 planets or a giant planet with 20 moons. The simulation calculates the gravitational pull between every single object at every single moment, tracking their movements forward through virtual time. But gravity alone is not enough. To capture tidal evolution, scientists must weave in additional algorithms that mathematically represent the stretching of a world, the lag of its tidal bulge, and the resulting transfer of energy and angular momentum. It is an immensely complex calculation requiring trillions of operations per second. This is why only the most powerful supercomputers on Earth can run these models with the necessary detail. The visualizations they produce are breathtaking. You can watch as a virtual moon, starting in a wide, elliptical orbit, begins a slow, graceful spiral inward toward its planet. You can witness the exact moment an orbital resonance locks into place, the orbits of 3 moons clicking into a perfect rhythm that suddenly amplifies their tidal heating, turning a cold ice ball into a world with a subsurface ocean. You can see a planet's fierce rotation gradually break, its day lengthening as it pushes its moons farther away into the dark. These simulations are our time machines. They allow us to rewind the solar system's history to test theories of how it formed. Did Jupiter's moons migrate into their current resonant chain, or were they born that way? By running the simulation backwards and forwards, we can see which initial conditions lead to the system we observe today. More importantly, they are our prediction engines for the thousands of exoplanet systems we are discovering. When we find a star with 2 giant planets orbiting very close together, we can plug their masses and distances into a tidal evolution model. The supercomputer can then tell us the likely future of that system. Will those planets spiral into their star in 1 billion years? Will they become tidally locked to each other? The simulation reveals the fate written in their gravitational code. This digital cosmos is where theory meets reality, allowing us to not just observe the heavens, but to understand their deepest, slowest rhythms. These supercomputer models are nothing without real data. They need the precise measurements of the universe, numbers fed in from the most sensitive instruments humanity has ever built. To observe the slow creep of tidal evolution, we have become masters of measuring the imperceptible. Our most precise ruler is light itself, fired across the solar system. For decades, observatories on Earth have been aiming powerful lasers at the retroreflector arrays left on the Moon by Apollo astronauts. By timing the round trip of that light pulse with picosecond accuracy, we know the distance to the Moon down to the millimeter. This lunar laser ranging is the gold standard, directly confirming the Moon's 3.8 centimeter annual retreat and the slowing of Earth's rotation. It is a daily experiment in celestial mechanics, proving tidal evolution is not just theory, but a measurable fact happening right now. For targets farther away, we use radar. Massive radio telescopes like the ones at Arecibo before its loss, and now the Green Bank telescope, beam powerful radio waves at nearby planets and their moons. By analyzing the faint echo that returns, we can map surface features with stunning detail, and more importantly for our story, measure their orbits and rotational states with incredible precision. This is how we know the exact orbital decay rate of Mars's moon Phobos, tracking its slow death spiral meter by meter. To see the grand choreography of the galaxy, we look to space. The European Space Agency's Gaia spacecraft is performing a census of over 1 billion stars. It does not just map their positions, it measures their tiny motions across the sky, a technique called astrometry. By watching how stars subtly wobble over years, Gaia can reveal the gravitational tug of unseen planets, and it can also detect the subtle distortions in binary star systems caused by their mutual tidal pulls. This gives us a statistical view of how common these gravitational dances are across the Milky Way, but perhaps the most elegant method involves watching stars wink. For eclipsing binary stars, systems where two stars orbit edge-on from our perspective and regularly eclipse each other, we study their light curve, the precise graph of their brightness over time. If the stars are close enough to be tidally distorted into egg shapes, their eclipses change character. The light dips become smoother, more rounded, betraying the distorted forms of the stars themselves. We apply the same principle to transiting exoplanets. As a planet passes in front of its star, the exact shape and timing of the dimming can hint if the planet is being stretched by its star's gravity, a telltale sign of intense tidal forces at work. Every millimeter measured by laser, every microsecond shift in a radar echo, every subtle wiggle in a star's position is a piece of data. This flood of information flows back into those supercomputer models, refining their algorithms, testing their predictions, and sometimes forcing a complete rethink. It is a virtuous cycle of discovery. Observation validates theory, and theory then tells us where and how to look next, sharpening our questions about the silent, patient forces that are, even now, rewriting the future of the cosmos. The data flowing from our telescopes paints a picture of countless locked worlds, but could we ever transform one of these silent globes into a home? Terraforming a tidally locked planet stands as the ultimate engineering challenge, a project that would demand not just planetary management, but a re-engineering of sunlight and climate on a stellar scale. The goal would be to break the tyranny of permanent day and night to create a world with a livable rhythm. One audacious concept involves building colossal orbital mirrors, vast reflective sails positioned at gravitational sweet spots like Lagrange points. These mirrors would not orbit the planet, but would instead orbit the star in sync with the planet, forever positioned to beam reflected sunlight onto the frozen night side. Picture a second artificial sun rising eternally over the dark hemisphere, its light carefully tuned to melt ice caps and warm the atmosphere without causing a runaway greenhouse effect. The engineering is mind-boggling, requiring materials stronger than anything we possess today and construction techniques in the hard vacuum of space that we can barely conceive of. But the mirrors are only the first piece of the climate puzzle. Even with a warmed night side, the planet's atmosphere would still struggle. Hot air from the scorching day side would rise, creating a permanent low-pressure zone, while cold, dense air would sink over the cooling night side. This extreme temperature difference would generate hurricane-force winds roaring perpetually from the day-night terminator line. To make the surface habitable, we would need to tame these winds, not eliminate them. Here, atmospheric engineering comes into play. We might seed the upper atmosphere with carefully designed particles or compounds to increase its thermal conductivity, helping to smooth out the temperature gradient. Another idea involves constructing continent-scale wind farms along the terminator, not just for power but as active elements in a global climate model. These immense structures could help break up and redirect the jet streams, creating more stable weather patterns in the twilight belt. The most promising area for settlement would be this very terminator zone, the ribbon of eternal sunrise or sunset circling the globe. Here, temperatures could be moderate with a perpetual golden light powered by the orbital mirrors. Entire civilizations could exist in this engineered twilight, their agriculture and cities stretching in a ring around the planet, forever walking the line between the fire and the ice. The sheer scale of such a project forces profound questions. The energy and material resources required would dwarf the entire economic output of Earth for centuries. It would be an endeavor for a unified, space-faring civilization with a motivation beyond mere survival, perhaps a deep ethical drive to create new homes for life. The ethical dimension is inescapable. Would we have the right to completely reshape a world that might already harbor its own simple, subsurface life in those hidden oceans? This is not gardening, it is planetary-scale genetic engineering applied to an entire biosphere. Furthermore, the project's timeline would span millennia, demanding a societal stability and long-term purpose that human history has never achieved. Any civilization that undertakes this would need to think in geological time, its commitment unwavering across generations. Yet, if it could be done, the reward is staggering, a testament to a species that learned to read the silent laws of tidal gravity and then rewrote them, turning a cosmic prison of eternal extremes into a cradle for a new dawn. The power to reshape orbits is a responsibility of staggering magnitude. With it, we would hold the future trajectories of worlds in our hands, a prospect as terrifying as it is magnificent. Before we ever fire a gravity tractor or deploy an orbital mirror, we must confront a profound ethical question, should we? The cosmos operates on a delicate clockwork of gravitational balances, many of which we are only beginning to understand. A seemingly beneficial act, like nudging a resource-rich asteroid into a stable Earth orbit for mining, could have cascading effects. That asteroid's new path might, over centuries, subtly perturb the orbits of nearby satellites or even other asteroids, setting off a chain reaction we cannot fully predict. The gravest risk lies in tampering with established orbital resonances, those precise gravitational rhythms that stabilize moons and generate life-giving heat. If we were to adjust the orbit of one moon in a resonant chain, like those around Jupiter, we might unintentionally break the rhythm. The result could be chaos, moons shifting into new, unstable orbits, potentially colliding with one another or plunging toward their planet. The very tidal heating that sustains a hidden ocean on a world like Europa could cease, freezing that potential cradle of life solid for eternity. Our well-intentioned engineering could inadvertently commit cosmic genocide on a scale we can barely comprehend. Science fiction has long wrestled with this dilemma. In stories like The Wandering Earth, humanity takes the ultimate step of moving our entire planet to escape a dying sun. The narrative focuses on the heroic effort, but the unspoken consequences are vast. What happens to the moon? What gravitational ripples does our displaced world send through the solar system as it journeys? These stories are thought experiments, forcing us to consider the second and third order effects of playing with celestial mechanics. This leads to a deeper philosophical divide. One perspective holds that the cosmic order, forged over billions of years, possesses a wisdom beyond our own. These orbits and resonances are the outcome of natural laws playing out over eons, resulting in a stable, if dynamic, equilibrium. To interfere is an act of profound hubris, akin to a child rearranging the gears of a master clock. We might see a single gear we want to move, but we cannot possibly understand the function of the entire mechanism. Perhaps some things, especially on the grand celestial scale, are meant to be left untouched, observed with humility rather than altered with ambition. The opposing view sees not hubris but destiny, Life itself is a rebellion against entropy, a constant fight to create order and sustain complexity. As the universe's only known self-aware matter, we have a duty to not just understand nature, but to protect it and ultimately to extend its gifts. If we can prevent an asteroid impact, should we not? If we can stabilize a climate on a dying world to preserve a unique biosphere, is that not our moral obligation? This view casts us not as meddling children, but as nascent stewards growing into our role as caretakers of solar systems. The ethical path likely lies not in absolute inaction nor in reckless ambition, but in a new kind of science, one that couples profound understanding with profound caution. It demands simulations of unprecedented depth, oversight spanning generations, and an international consensus that places the stability of celestial systems above any nation's or corporation's gain. The question is not merely whether we can steer an orbit, but whether we have cultivated the wisdom to know when and for whom we should. The silent clockwork of the cosmos has long been a canvas for our stories. Science fiction, in its quest for spectacle and wonder, has often seized upon the immense power of tidal forces, sometimes bending the physics for dramatic effect while accidentally spotlighting the very real anxieties of a gravity-shaped universe. One of the most chilling early explorations aired in an episode of The Twilight Zone titled The Midnight Sun. In this story, Earth has been knocked from its orbit and is spiraling inexorably toward the Sun. The episode masterfully captures the psychological horror of a tidally locked scenario in the making. As the planet's rotation slows, one hemisphere becomes a permanent, scorching day. The concept of a fixed, deadly sun hanging motionless in a blanched sky is a powerful metaphor for the climate extremes a locked world could face, even if the mechanism, a sudden orbital shift, is more poetic license than plausible astrophysics. The true terror lies not in the incorrect orbital mechanics, but in the devastatingly accurate portrayal of a world losing its rhythm, where the simple, reliable cycle of day and night is replaced by a permanent, inescapable sentence. A more recent and visually stunning depiction gave audiences a visceral, if flawed, sense of tidal scale. In the film Interstellar, the crew visits a planet orbiting close to a supermassive black hole, Gargantua. The planet is gripped by colossal, mountain-sized waves that circle the globe. The film suggests these are tidal waves caused by the black hole's ferocious gravity. While the visual is unforgettable, the science is exaggerated for cinematic punch. In reality, a planet that close to a black hole would be tidally locked almost instantly, with one side perpetually facing the monster. Any ocean would likely be pulled into a stable, elongated shape, not a traveling wave. Furthermore, the energy required to propel water kilometers into the sky would likely tear the planet itself apart. Yet, the scene succeeds brilliantly in conveying a core truth: the sheer, humbling, destructive power of extreme gravity. It translates an abstract orbital force into something you can feel in your gut, a wall of water representing the universe's indifference. For a more rigorously imagined future, we turn to authors like Kim Stanley Robinson. In his novel 232, part of his Mars trilogy, he presents a meticulously terraformed Mars where the moon Phobos and its orbital decay are not just backdrop but a central plot point. The characters discuss Phobos's fate with accurate numbers, treating its slow spiral not as a sudden catastrophe, but as a long-term environmental and engineering problem to be managed. This reflects a shift from using tides as a sudden disaster trigger to treating them as a persistent, slow variable in planetary climate and development, a challenge for future civilizations to measure, model, and perhaps mitigate. It is science fiction that leans into the forecast, not the fantasy. The gap between Hollywood's spectacular waves and a novelist's detailed orbital calculations is where our real understanding lies. These stories, whether exaggerated or precise, serve a vital purpose. They ignite curiosity. They make us ask the right questions. After seeing a terrifying tidal wave on screen, a viewer might wonder, could that really happen? The search for that answer leads straight into the real mechanics of Roche limits, orbital resonance, and tidal heating. Science fiction provides the emotional hook, the sense of awe and danger, while science itself provides the deeper, more patient narrative of gravitational relationships unfolding over eons. One gives us the adrenaline of a crashing wave, the other reveals the slow, silent current that has been pulling on it for a billion years. Both are essential to envisioning our place in a cosmos where the gentle tug of a moon can, given enough time, remake a world. The immense forces sculpting moons and stars leave us untouched in our daily lives. We do not feel the Earth's rotation slow by a sliver of a second each century. We cannot sense the moon's annual retreat, a distance smaller than the length of your hand. This is the great disconnect between cosmic reality and human perception, all because of time. Tidal evolution operates on a timescale that dwarfs human history, making its effects feel invisible, like watching a mountain erode by a single grain of sand each year. The forces are colossal, but the changes they produce are distributed over such staggering eons that they become imperceptible within a single lifetime, or even across the entire span of civilization. Consider the drift of our continents, a process called plate tectonics. The ground beneath your feet is in constant, slow motion, but it moves at about the same speed your fingernails grow. You will never feel the shift, yet over millions of years, it remakes the map of the world, pushing up mountain ranges and opening vast oceans. Tidal orbital changes are similar, a geological patience applied to the heavens. The 3.8 centimeters the moon moves away each year is trivial now, but multiply it. Over the course of 1 million years, that tiny annual drift adds up to 38 kilometers. Over 100 million years, it is 3,800 kilometers, fundamentally altering the appearance of our night sky. We are like mayflies living on the face of a grand, ancient clock, witnessing only a frozen snapshot of its hands. Our entire recorded history is but a single tick in a mechanism that measures time in billions of years. This perspective does not diminish the reality of the process, it elevates the achievement of our understanding. That we can measure the millimeter shift of a world, calculate the slowing spin of a planet, and predict the fate of moons millions of years hence is a triumph of human curiosity and ingenuity. We have learned to see the grain of sand falling from the mountain, and in doing so, we have grasped the patient, relentless power that will one day level it entirely. From the subtle drag of a tidal bulge to the cataclysmic merger of black holes, we have traced a single, elegant force. This is the quiet heartbeat of the cosmos, a gravitational rhythm that writes the long-term destiny of every world. Tidal evolution is not a rare event, it is the universal sculptor. It carves the orbits of moons, it forges hidden oceans under ice, it locks planets to their dim red suns, and it choreographs the final, fiery waltz of dying stars. From the 3.8 centimeters our moon drifts each year to the final ring of light around a future Saturn. The process is the same, only the scale and the time frame change. We stand at a remarkable point in this story, no longer just passive observers of these celestial tides. We measure the millimeter retreat of the moon with lasers. We predict the demise of Phobos with radar. We listen to the chirp of neutron stars decaying through gravitational waves, and we begin to dream of a day when this understanding becomes a tool, a way to gently nudge an asteroid from its path or perhaps in the far future to stabilize an orbit for a new home. The universe is not static, it is a slow-motion ballet of gravity and time. Our role is to keep watching, to keep questioning. Every new exoplanet discovered, every subtle wobble of a star measured, adds another piece to this grand puzzle. We must continue to imagine, to calculate, and to wonder. For in learning the steps of this ancient cosmic dance, we may one day learn to move with it, to harmonize our own fleeting existence with the patient, powerful rhythms that have shaped the heavens since the very first light.